going over, high-level stuff. So I can't play audio off of this thing, so you'll be spared the playing the various audios that I did for the other class. So here is the summary of what was in our homework VM. There were about 8 rootkits leveraging about 10 techniques. And I use the term rootkit loosely. Some of them were just really proof of concept using one technique or another. And so the tip of the hat was to everyone who did the homework, and the wag of the finger was to people who didn't give me one. Do you have one for me? Okay, excellent. All right, good. No wag of the finger for you. All right. So I said, if you had happened to, stumble upon the, quote, right detectors, then you would see a lot of stuff. And I said one of my favorite ones prior to having found Varus Block Ada was Gmer. So the question is, what if we run Gmer on this VM? What all are we going to see? And so that's what we're going to do now. So go back out to your virtual machine. You should now have it, popped up to this zone alarm thing. And from there, you can go allow into trusted zone, and then hit OK. And then after a little bit, it should have internet access. So what we're going to do is we're actually going to, from within the system, so remember the hypothetical scenario here was, you're at someone's pulled you in, they said, you're the security guy, come fix this thing, it's acting weird. And so you're doing a quick triage and saying, whether or not there's anything infecting the system. So while you want to be mindful of, whether or not you're going to have to do any sort of full forensic analysis later, you can at least do some basic checks initially. And yeah. So to that end, something we might do is pull down a tool like Gmer and run it actually on the system. So we're going to go to the internet and go grab Gmer and save it onto our system, as long as it allows it. So open up Internet Explorer, and we're going to go to www.gmer.net. And hopefully, this version of Internet Explorer isn't going to be blocked with a proxy or anything. And so if it asks you suggested sites, they don't turn on and then cancel. Right, and we see we got all sorts of extra great stuff installed by Zone Alarm, and we've got this rapport button right there. So our third-party software is nice and all up in our face, just like usual. All right, so www.gmer.net. I'm going to scroll down. There's going to be a download exe button. Click on that. It's going to randomly generate a name because they know that some stuff is looking for gmer.exe, so they randomly generate a name. Save it to your desktop. And then once it's saved, go ahead and hit run. All right, so it does basically a quick scan when you first load it up, and it checks any places that it thinks are obvious things that shouldn't necessarily be changing, just to try to give you a quick look to see if anything's bad there. All right, so I can see a couple things in red. It's only ever going to pop up this, we have found rootkit modifications if it has one of these red changes where it says, like, this is something I know there's a rootkit that makes this specific change. And so in this case, it found Hacker Defender, and it also found this other miscellaneous hidden process. But we can see it has a hidden process and hidden services, and the two hidden services are called Hacker Defender 100 and Hacker Defender Driver 100, stuff like that. And it found other various changes, but only for those red ones is it really saying, I know this is a rootkit for sure. And that's why, some of the other rootkit detectors as well would have, they would have highlighted things like Hacker Defender and Vanquish and stuff like that. They say, I know this is definitely a rootkit. And so some of them really err on the side of only telling you about things they really know for sure. They don't want any false positives, essentially, right? Some of them err on the side of no false positives. Some of them, like Gmer, they're erring on the side of no false negatives. And So they're trying to show you everything. And for no false negatives, they're assuming that you can look through the results and make the determination yourself. So they're going to show you a bunch of stuff, and then it's going to be up to you to determine whether it's good or bad. All right, so it says, do you want to full scan your system? Go ahead and hit yes. Now it's going to actually look at everything, not just that sort of summary view. It's going to look at everything on your system. It's going to tell you all the changes it sees, and now it's kind of up to you in order to decide whether that's a good change, a bad change, what caused the change, and for instance, how do you remove it. So we've got a bunch of SSDT changes. I talked about that briefly. That's the system service descriptor table. That's the interface between user space and kernel. All right, but we don't care about that so much for now. What we care about is if you scroll down, you'll see some changes like int for interrupt. And so it's saying int E, int 62, int 82, things like that. And that's saying right now, the interrupt descriptor table at descriptor index E, index 62, index 82, those are pointing at locations that I don't think this should be pointing at. So it has some expectation about what the system should look like. And it's saying this differs from my, basically static expectation. And so these are things which it's highlighting. There's other things, So this we kind of know about interrupt descriptor table, so we're going to focus on that one first. There's other stuff like this .text right here. That's saying in the .text section of ntkernelpa.exe, there's a change, and 12 bytes have changed, or 4 bytes have changed, etc. And this is that inline hook where we said an attacker goes in and they put a jump instruction or they put anything else. And so we know about inline hooks to the degree that we've seen in intro x86 class. We know what instructions are, so we certainly could go over and look at those specific instructions and see what they do. All right, so that's all I want to say about here. You can see there's obviously a ton of stuff. It's right now still searching through the import address table of all the open processes. So we know about IAT hooks as well from like binaries. But there's a ton of stuff that's changed on the system, and so now it's kind of up to us to say, is it good, is it bad, whatever. All right, so back here, I'm going to go back to my slides and kind of dig down into this. All right, so we know about the interrupt descriptor table from intermediate x86 class. We said it's basically an array. You can think of it like it's an array of function pointers saying this is the function which should actually execute when a particular interrupt occurs. We know that interrupts come from software sources or hardware. And so the hardware could be things like keystrokes, network activity, mouse movement, file system activity, things like that. So we saw one thing at the very end of intermediate x86 class. We showed an example of hooking the IDT in order to intercept keystrokes. So we basically installed a simple IDT-based keystroke logger. Now, were you to go back and run that example from intermediate x86 class and then install Gmer on your system and run it, what you'd see is something like this. Gmer would detect that, okay, interrupt 93, which happens to correspond to the keystroke interrupt, that thing is pointing at this new module, keysniff.sys, and this particular address. And so it's not pointing at the normal Windows keystroke handler that we expect. That's what we would see with that, but this is what we currently see with our VM. We see int E, and it doesn't actually know what it's pointing at, and it says just, here's a function pointer, that's where that thing's going to execute code, but we don't know what that is. So here what it did was it said, for this F9, F3A, blah, 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 it said, I know that that address is between the bounds of keysniff.sys. So keysniff starts here, ends here, and that address is somewhere in the middle. So it's trying to help you out and say, that function pointer points at that particular module. In this case, in our VM, it can't even figure out where it is. So it may be pointing into dynamically allocated memory. It may be pointing into a hidden process, stuff like that. But so as the quick review of segmentation from what we learned in intermediate x86 class, and segmentation and how it relates to interrupts and all that sort of thing, we said that you have 6 segmentation registers in 32-bit systems, and the segment registers point at some segment descriptor in the GDT or LDT, and the descriptor basically says, here's a chunk of memory, and it starts here and it ends there. But what we found at the very end was that although these can be used to, create granular access to memory, modern operating systems tend to just make one big code segment, which goes from 0 to FFF, covering all of memory. And they make one big data segment, which goes from 0 to FFF, call it covering all of memory. And so code and data for kernel are both set as ring 0, and they're covering all of memory. And code and data for user space are both set as ring 3, and they're just covering all of memory. And so when it switches between kernel and user space, it just changes the segment selector to, or it changes the segment registers to have a different segment selector, which points at a different segment, which says ring 0 or ring 3. All right, so this is basically how it worked. We said that in reality, all memory accesses on the system are logical addresses. Logical addresses were those 48-bit things where you have a segment selector which says this address starts at this particular segment, so it selects a segment descriptor out of the GDT or something like that. It says, I need to, start at this segment, and the segment descriptor has a base address. And like I said, for most of the time, the things we care about, all code and data is typically based at 0. But the segment selector selects this. This is based at 0, and then it says 0 plus some 32-bit offset equals the linear address or virtual address where we actually want to access. So people tend to think of, virtual memory access as just that 32-bit field that you see in various assembly instructions. But behind the scenes, whether explicitly or implicitly, you're always using one of the segment registers. All code access goes through the CS register. All data access goes through the SS register. And they're always selecting one of these 0-based segments, which then is added to the 32-bit offset. And so we just said there's, in this specific segment selector, there's a table indicator bit which says, is it using the GDT for this index or is it using the LDT? We said Windows doesn't use the LDT, so we don't have to care about that. We can always assume it's the GDT. All right. The actual segment descriptor inside of the GDT looks like this. There is a 32-bit base address, and like I said, that's mostly 0. Base address is 0, segment limit, that's 20 bits, but that can have a granular, those 20 bits can be modified by the granularity field. So if the granularity is set to, I think it's 0, then it's in bytes. This 20 bits is in, sizes of bytes. And if it's set to 1, then it's in sizes of 4 kilobyte chunks. So that means the segment limit typically is set to 4 kilobyte chunks. So you have a base of 0, you have a maximum segment limit times 4 kilobytes equals basically the 4 gigabyte space. So it starts at 0, goes to 4 gigabytes. All right. Now, how that relates to the IDT is that you have a specific IDT register that says where your interrupt table always is. And that's a 48-bit thing that says, here's my base of my IDT, and here's the limit. So typically IDT has 256 entries, but it need not necessarily. They could just say, the limit is such that it only has 32 entries or whatever. And each element of the IDT is, in reality, a logical address. And this is the key thing here, because this will relate to a different attack later. The entries are actually logical addresses, so they have a segment selector and a 32-bit offset. So an interrupt can actually occur in any context. You can just say, I want to occur in this segment context. I want to occur in that segment context. And then that base of whatever segment it's selecting will be added to the offset to get the linear address where it's actually going to execute code when an interrupt occurs. Now, normally when an attacker is changing the IDT, they basically focus on those two pieces of the 32-bit offset. And they say, okay, well, normally this points at, the kernel, and I'm going to change those two pieces to point at my 32-bit offset, because they're basically going to assume that the segment selector is always pointing at a 0-based segment. So this is the total picture. When you have an interrupt occurring, the hardware goes and it says, okay, where's the IDTR? Say that my interrupt table is. Finds the interrupt table, goes into the entry, whatever index for the interrupt that's occurring now, goes in, finds the entry, and that entry, like we said right here, is has a logical address in it. So then you take that logical address, take the segment selector, which points you at a specific segment, take the base plus the 32-bit offset, and you get a virtual memory address. That's where the interrupt occurs. That's where the code which handles the interrupt is located. And this is just a different way of saying it. All right, so in the intermediate class, we did the Pearly Gates lab where we installed a plugin into WinDebug. And this was the descriptor plugin, and all its job was to do was dump the GDT or dump the IDT. So we could use something like WinDebug in order to go in and inspect the IDT and manually say something's off about it. But we don't really need to, because things like Gmer will tell us this IDT is not pointing where it should be, or this IDT entry. All right. So I don't know if this is accurate right now. I'm going to go check it in a second. But at least in one version of this, well, I should just go check it. All right. So we have int e, and we have the address, which is actually being targeted. Let's see in the VM. All right. So it's done running. In the VM, let's see if there's any hidden processes. All right, so I said one reason why it could be saying, it doesn't know where the data is, or it doesn't know what module this is associated with. It could be because there's a hidden process, or it could be because it's allocated in dynamically allocated memory. So I'm going to see if this thing says there's any other hidden processes which are roughly in that memory range. This is the inefficient way to do it. Straightforward way. There we go. All right. So what we're looking for is the number. I'm going to write this on the board just so I can remember it. F8B F28. All right, so that's what we're looking for. We're saying this, when you have interrupt E occurs, it's going to jump to address F8B, F2, whatever. And I have some hidden processes down below, nicely highlighted in red. So there's one of them, mmpc.sys, where it starts at F8B, F2, 000, and it goes to F8B, F4, 000. So F8B2816 is definitely within that range, right? So right now we know that interrupt E is actually transitioning to this hidden driver, mmpc.sys. So this is a case where I can't remember if I am actually using decom in order to hide this or whether it hides itself naturally, but this is a case where there's a kernel driver which is being hidden from the list of kernel drivers. It's been unlinked from one of those linked lists. So we only showed the linked list that has to do with processes, but there's also linked lists for all the loaded kernel modules, all the DLLs in a process, stuff like that. So it's been unlinked, and whatever it is right now, whatever this MMPC does, it's hooking the int E. So if we were going to investigate this and say, what is it doing? Well, we can obviously go directly to int E and just, start looking at the assembly code and just reverse engineer it. But like I said, that's too advanced for this class. So we're going to start with, one other hint. We also need to look up what is that int E, So we need to, you could just Google this. You could say, what is interrupt E on Windows? Google that, and you'd probably find something coming back with that is the page fault handler. So what I did here is I just pulled this from the intermediate x86 class. When we were talking about interrupts, we said for the entries below interrupt 32, they have some by convention values assigned by Intel. So specifically, the convention value for vector number 14, and 14 is decimal version for hex E. This is the page fault handler. So now we have some malware which is hooking the page fault handler. Page fault handler, like we said, is the thing which is responsible for when you're trying to access some virtual memory, but some other sort of error condition occurred. It's responsible for figuring out, is this a recoverable error condition or is this unrecoverable? We said recoverable things are like, the bit is set to not present, but it turns out that the metadata on the particular page entry says, hey, this chunk of memory is actually out on disk in my page file right now. So it's just, the OS ran out of memory. It had to swap some chunk of physical memory out to disk because it's not being used right now. That's a recoverable one. There's other cases where someone's trying to write to read-only memory. That potentially is recoverable. There's other cases, well, for copy on write, like we talked about last time. There's other cases where, for instance, we talked about the NX bit, where that's the no execute bit, and you set that on something like the stack, and you say, I don't want anyone executing code on my stack. And so if they try to execute code, it's going to cause a page fault. The page fault handler will try to recover that. So, but, you know, the fact is, we talked about someone in the intermediate x86 class who might be interested in hooking the page fault handler, and that was Shadowwalker. Right, so we said all that discussion of paging and all that, it was all just an elaborate ruse to get you to the point where you could understand something like Shadowwalker, should you ever see it. We said the point of Shadowwalker was it exploited the fact that for these virtual to physical translations, there's something called the TLB, the translation look-aside buffer, which is just a cache. It says this virtual number goes to this physical number, and that's kind of what this picture is trying to say. It's saying maybe there's virtual address 120000, something like that. 12 and then 3 zeros. Maybe the virtual address 12000 translates to physical address 1000, right? That information will get cached in the TLB so that the hardware doesn't always have to go walk those page tables, right? We said in the case of GDT and stuff like that, there's caching mechanisms in order to prevent it from having to walk tables all the time. In the case of paging, the TLB is all about caching information so that you don't have to walk page tables. And what the attacker was doing in the Shadowwalker case is they were saying, okay, it turns out there's actually two caches. There's one for data access and there's one for code access. So that first one, the ITLB, that's code access, instruction translation look-aside buffer. It caches when it sees someone trying to execute code on a particular page of memory. It caches, you know, this virtual memory went to that physical memory. But if it sees someone trying to read data on a particular virtual memory address, the DTLB, data translation look-aside buffer, caches the mapping, this virtual address goes to that physical address. And so specifically, Shadowwalker would hook the page fault handler, and it would say, okay, if I'm trying to access my own code, if I'm trying to execute my code, I will map my virtual address to the correct physical address where my code is located. However, if some other thing, like the security software, is trying to read my code, it's trying to read my virtual memory, then that's a data access, and I will map that to some garbage frame, right? So it splits this off so that people who are trying to read data get different results than people who are trying to do code. And so this int e hook is basically the thing which says, you know, who's trying to access my data right now. So it always marks its, you know, when it's done executing its own code, it marks itself as not present so that anyone, code or data, that tries to access its own code will cause a page fault. It's saying, I'm not here anymore. This isn't a valid mapping. And then the page fault handler is supposed to sort it out. But it becomes the page fault handler in order to sort it out and say, if I'm trying to access my code, go ahead and let me do it. Otherwise, I will put it to garbage. So, in this particular case, although this is, you know, an interesting attack and everything, the page fault handler has a known value, right? So this IDT entry should always point at the OS's page fault handler. And similarly, although you could manipulate this, you could put an inline jump rather than changing the IDT. You could put an inline jump at the page fault handler. Again, that code has a static value, and so you could still detect it. So it's an interesting way to, you know, try to hide, you know, physical memory when being accessed as virtual memory, but it's still ultimately detectable. All right, so that's one thing we could, you know, sort of know about by leveraging some of our knowledge of the previous thing. Really, though, in order to get into that and say this is Shadowwalker, you kind of have to go in and look at the assembly instructions. So that's why I have that TiddlyWiki thing that actually does go in, analyze the instructions, and say, okay, what's that doing? What's that doing? What's that doing? And then you can see quite clearly that it's looking for things like user space versus kernel space access, read access versus write access, code access versus data access. All right, but this is just an example where, you know, Gmer tells us something, but we still have to have extra information to go dig down into that more. All right. And so there's this one other sort of ambiguous entry here, and I just referenced this just to fill in this little thing here. This is actually due to Shadow Walker, and I don't think, unlike it says here, I don't think it's due to it hiding another kernel module. I think it's just due to some of its own changes that it makes. I need to go confirm that again. But this is an example where sometimes the tools are a little too ambiguous, and they turn out to be, you know, what can I do? What is this data supposed to tell me? What can I do about it? How am I detecting something? You know, it's putting it in red, so it's saying this is really bad, but I don't know what to do with that. And I was wondering about that for a while, so I emailed the author. And he said that the number is actually an eProcess structure pointer. He's saying it can't identify the name of the structure, but it's some type of structure where it's been unlinked, for instance. So, all right. So there's some other information we could know about from the intermediate x86 class, but it turns out Gmer doesn't actually show us this information. So we're going to have to use a different tool for that. We're going to use Toluca, which is a newer anti-rootkit detection tool from Russia. I should say that Gmer is from Poland. If you have any sponsors that care about where the origin of your code is when you're running it on their system. Gmer is from Poland, Toluca is from Russia. So what we're going to be specifically looking for here is a call gate, and we've seen call gates in only this most recent version of intermediate x86, basically just because I wanted to talk about it in the rootkits class. So let's go back into our VM. We're going to just minimize Gmer for now. We're going to go get Toluca. I think it's at www.toluca.org. Yes. TULUKA.org. Then once you're there, there's going to be a download option on the sidebar. And then just download the version that it gives you onto your desktop again. So you should be getting 1.0.394.77. Leave it on your desktop. When it's done, go ahead and open the zip, extract it, drop it on your desktop again. Now Toluca is actually going to try to speak out over the network. Go ahead and say no, don't allow that. I haven't looked into why it's doing that yet. I'm guessing like VirusBlock Ada, it may be trying to do some digital signature checks, but I don't know. You don't know until you look, right? So for now, it's nice benefit that we have zone alarm on there that we can say, don't allow this to talk out over the network. Random programs from Russia. All right. So when it's all downloaded and extracted and put on your desktop, just go ahead and run it. There you go. There's zone alarm trying to do the DNS query. They deny. Remember this setting. So I mean, I like Toluca's interface. It's pretty good. Has things broken up nice, right? So here we go. We can see there's some suspicious processes. There's that hid 0 for system that I said I hid. I said I hid the system process. You got hacker defender hidden there. That's good. So I mean, it's nice. It makes it stand out at you. It shows you everything that's there. Now, in Gmer's defense, if I go back to Gmer, there's this little arrows thing at the top window. If you click that, you can expand it, and then you can also see a similar sort of interface where you can look at all the processes, and it'll show they're all hidden. And here's all the modules. I can see there's my hidden modules at the bottom there. So you can break stuff up like this in Gmer as well. But going back to Toluca, so the one thing, like I said, that Gmer is not looking at, it's not looking at anything in the GDT. So we saw in the intermediate x86 class that call gates are a way that we're sort of put in there to allow, I believe they were put there basically to allow for that same sort of user space to kernel space communication that ultimately got ended up being done with interrupts or sysenter command. But it's basically something where the kernel creates a specific call gate type entry in the GDT, And what it does is that entry, it looks very much like a IDT entry. Let's see if I have a review. Yep, there it is. Right, so call gates look very much like an IDT entry in that they have a segment selector and a 32-bit offset. So they're specifying a far pointer where if you call to this call gate, it will go and vector code to that location. It's got some DPL stuff, so you can say, what privilege is allowed to execute it, etc. And so a call gate is something where the kernel would say, I will allow user space to call this call gate to jump to this specific function. And that function would potentially be a function which checks EAX to say which system call are you trying to do, right? So it's one specific way. But if an attacker puts a call gate in, then this can kind of be like a backdoor communication mechanism from user space to kernel, where they can execute this call gate in order to target some specific code in kernel. They can target existing code, they can target their own code, things like that. Although I haven't yet played with targeting existing code because I'm curious what level of capability you can get out of that. So that's call gates. Yeah, that's just another review thing. Okay, so the funny thing is, we'll come back to Tuluka in a second here, but if you were to close Gmer now, and you were to run Gmer again while Tuluka is running, what you'll find is that Tuluka actually also hooks int E, and it hides its process and stuff like this. This is kind of par for course in that, I said Gmer is changing its name as you download it because they're worried about people looking for and killing gmer.exe. Tuluka, similar kind of thing. They're worried about malware going after Tuluka, so they're hiding themselves so that the malware needs to be, coming in. And malware could very easily get around that sort of thing, but whatever. There you go. A rootkit in your rootkit. I really want to go, when I have spare time, I'm going to go look at what exactly their int E hook is doing to see. I would expect they're probably trying to see when data is being paged in and out of memory so that they can see, hey, is there some executable code that's getting pulled back in from disk that I don't know about? So I expect it for something like that, but I don't know. All right, so just to go back to Gmer, or Tuluka for a second. Now maybe I'll come back to it when we have new types of things to look about. All right, so another thing that you would see plenty of in Gmer or Tuluka is import address table hooks. So they'll show up like that in Gmer. Let's see. Gmer, if you go to the Rootkits malware tab, you have all of those right there. Okay. Over here where it says type, it says IAT. That's saying for something, it could be user space, it could be kernel space. Let me find one of both. All right, so this right here is saying we have an IAT hook, and it's in this particular module, System32 drivers, ndis uio.sys, or up here it's in tcp/ip.sys. Let's say that, that's an easier one. Right, so it's saying in the import address table of tcp/ip.sys. So that's the thing which implements your TCP/IP protocol in the kernel. It's saying that this thing imported the function ndis.sys, ndis register protocol. So TCP/IP.sys is asking for the function ndis register protocol from the ndis.sys module. So it's importing it. But then it's saying, in reality, that import address table for that particular entry, ndis register protocol, is currently pointing at F4, B8, blah, blah, blah. And that's actually pointing at, I'll expand this over to the side. It's actually pointing at vsdata.nt.sys, which is zone alarm kernel module. So zone alarm in this case has gone in there and it said, I'm going to hook the import address table of your TCP/IP.sys so that if that thing ever calls ndis register protocol, it's instead going to call me. And so zone alarm is basically trying to put itself in there to try to intercept calls to things which are adding new network devices, essentially, or network drivers. So it's kind of, the firewall is kind of concerned. It's saying, is anyone else registering a new network device? Because if it's not aware of that, then a network device could potentially register itself to find out about traffic before this firewall thing does, right? And then it could hide traffic from zone alarm. That's a kernel space IAT hook. Same thing can happen in user space. So I don't know, here we've got mysqld.exe running inside the VM. That's left over from the immediate x86 class and other stuff. It's saying that mysqld, if I'm interpreting this thing correctly, mysqld.exe has loaded in its memory space user32.dll. User32.dll imports this function load library xw from kernel32.dll. Right, so we've got MySQL as the library user32. User32 imports a function from kernel32, and for that particular function, the IAT entry has been redirected so that it looks like, again, zone alarm has pointed that function at iswshex.dll and stuff like that. So there's a user space DLL that zone alarm is injecting into all the processes, and it's going in, hooking the import address table, and redirecting control over to their thing. In this particular case, it's worried about load library, which is a function we talked about a little bit in Life of Binaries, which loads up new DLLs. So again, zone alarm is worried that if this thing can call loading up a new DLL, what if that DLL is allowed to call some function without its knowledge? So it wants to go ahead and hook any new DLLs that get loaded at the time they get hooked, or at the time they get loaded. So it's just basically trying to maintain control, and so it's having to spread these hooks far and wide in order to maintain, make sure nothing slips by it and loads something that can send network data without it being intercepted. And that's sort of what I was talking about, Microsoft not liking people using these unsupported methods. And actually, I should probably note to self, I should probably look up whether they use, does anyone know, do you guys know if they check the IAT with patch card? No? All right, so IAT, just to refresh your memory from Life of Binaries. So this was the overall binary structure. We had DOS header up here, and then file header, and optional header that's not optional. And then there were a bunch of, there were sort of 15 out of 16 of the entries at the very end of this particular optional header. Those are point at specific types of data inside the file. And the one we're caring about here is there's an entry at index 1, which points at, it says, here's where your import data is. This will eventually get you to the table that has all those function pointers, right? So that import data points at a new structure, these image import descriptors. And so there was one of these descriptors per DLL or module that you're importing from. So, this would be like, this would say, and I'm importing user32.dll, and this would say I'm importing kernel32.dll, and that would say I'm importing ntdll.dll. There's this name field, and so for each of these structures, the name will point out and say, this is the name of the module I'm importing. So one of those per each thing. I don't care about that so much. And then that eventually points at these data structures, which is sort of an overloaded union, which can point, one of the interpretations of this is that it will point at this type of field, a hint and a name, and that's what we're actually going to see here. So this is what I think is the more useful look at this. So this right here, there's an image import descriptor, and I said there's one of these per DLL you're importing from. And so this is in an array, and there's maybe a null terminating entry in the array. Right now, this is, I don't remember what I pulled this in from, but this is something that only imports something from NTOS kernel.exe. So this is a kernel module doing some imports. It says, I need to import some functions from NTOS kernel.exe. One of the fields in this image import descriptor points at this array, which is the import names table. So the names table always points at these other structures, which start with a hint, which is we don't care about for now. So it's sort of a hint and then a string. And so that string is saying this is the function I want to import. And all that data is just there for the OS loader so that when you double click on an exe or whatever, when you open any sort of module, a P file, the OS loader needs to go to this import address, import names table, and say, here's all of the functions this thing needs to operate correctly. So it needs to go out and find those functions. In this case, it would go out to NTOS kernel. It would have to consult its exports and it would say, where are you exporting IO delete symbolic link? Where are you exporting IOF complete request and stuff like that? And for each of those locations in NTOS kernel, it grabs the virtual address and it's going to stick it into the import address table. So whereas the import address table on disk just points at the same data structure, when the OS loader runs around and fills it in memory, this import address table gets filled in with pointers that point out to NTOS kernel, or, yeah, I don't have the other example, so, or HAL.dll or whatever. And so that thing right there at the end, at this top corner, this is the table where something like zone alarm is filling in those pointers so that they point at their code rather than the original code from mdis.sys or kernel32.dll or whatever. So this is sort of, we learned about imports in like binaries. It all comes down to this table right here becomes a target because it gets set up once at initialization. The OS sets it up, but it should never change after that because the function is where the function is. And if the attacker comes in and changes that, then he redirects control flow to his own stuff. And there's the equivalent of this in Linux as well. It's like .got.plt or something like that, where it's again just a mechanism by which there's eventually going to be some big table of where the code should be pointing. All right, and we did actually cover one example of IET hooking in like binaries, so you can go see that if you'd like. And I guess the key point here is that, well, what I should say is this IET hooking is one of the sort of two main mechanisms that get used for user space rootkits. So your Ring 3 rootkits. DLL injection plus these various hooking techniques are how you can enable hiding just in user space. So DLL injection, if you go to Wikipedia, you'll see there's a bunch of different ways to do DLL injection on Windows as well as Linux. But what it means is that the attacker gets some code in the memory space of the process that they want to hide stuff from. So that could be taskmanager.exe in the example we did. We used, just one mechanism, the app-init DLLs, which is the simple, easy, lazy way. You put a DLL into that registry key, and it automatically gets put into the memory space of anything that loads user32.dll. But the point is, DLLs can have essentially main functions. There's an initialization function where when the OS loads the DLL into memory, it calls the main of the DLL. And when they call the main of the DLL, that means if this is an attacker DLL, it means the attacker is running code in the process space of the program, and they can run around and change the import address table, change export address tables, put inline hooks. And so those are kind of, the two main ways are really import address table hooking, where malicious DLL gets loaded, attacker redirects to that. And malicious DLL gets loaded, and attacker goes in and puts jump instructions, for instance, which redirect to that. So either IET hooks or, actually I think that's probably the next section. Yeah, IET hooks or inline hooks. So inline hooks, this is sort of the breakdown. I probably should make a breakdown slide for that IET entry as well. All right, so another thing we see in Gmer is a bunch of things with that are inline hooks, but sometimes it might not be as clear that they're an inline hook. So all these ones where it says .text, what it's trying to tell you is this is the section in the PE where I see an inline hook. And the thing is, it need not always be .text. We said by convention, typically compilers name their code section .text, whether it's Linux or Windows or anything else. But there can be other sections, like I think we'll see something up here. There we go. This one right here, it's a page section. So on Windows kernel drivers, typically the .text section means code which should never be paged out to disk. So the compiler marks those as non-pageable. So that code doesn't get kicked out of disk, because you can have things like, say you have an interrupt handler. You don't want that out to disk at the time the interrupt occurs, because the page fault handler can't get kicked off at that point, and then it can't deal with that. So the page is just another section in the binary. So if we were to go look at the P headers of nt kernel.pa.exe, we'd see there's .text section, .data section, .rdata section, .page, .page lkd, etc. And so this is just saying at the section page in the binary ntKernelPA.exe, corresponding to a specific function, this ZW query value key in this particular case, plus some offset. So it's saying the nearest, it tries to basically figure out which symbol this is related to. So in some cases, inline hooks will be, immediately at the beginning of a function. So that would be when you have a symbol where you know it's there, you'll have a jump instruction right at the beginning of the function. In other cases, either A, it may not know the function name, and therefore it just tries to find the closest thing, or B, they could put inline hooks later on in the function. But if we were to scroll over, then there's all this extra information, but I'll just, and actually, I'll just say this quick right here before I go break this down. This is the one change where you wouldn't see this change if you were to reboot the system before you did an appropriate check. So this change right here, it's saying, all right, let's look at this. In the .text section, oh, okay, sorry. I'm going to leave that there. I'm going to go break down these changes, and then we'll come back to that. All right. The way that you interpret Gmer's description of the changes is, the first column is the section in which the hook resides. The second one is the process, or DLL. I think it's just process in which the hook resides, because they'll say process ID, and then there'll be this module. So if it's not actually the task, so this was like taskmanager.exe. If it's not actually task manager, which is being hooked, then it'll say, okay, it's actually ntdll.dll, which is being hooked. And specifically the function ntcreate file. It's the function name. And then the address where the hook occurs. And that's the literal address. And then the number of bytes that changed. And in this case, I'm pretty sure this is like an error. And if I had, so it's saying 1 byte and it's saying E9. Just a single byte E9 change wouldn't do anything. In fact, it would probably break stuff. I'm almost certain it would break stuff. I'm pretty sure I had seen with these things where if I rescanned it, I got a clean result. I'm pretty sure there's a jump instruction there right now, and E9 is the first byte of a jump instruction, so I think it just had an error where it's trying to say there's a jump change, but had an error. But anyways, if it can, it tries to interpret those bytes as an instruction. So with these other ones where it succeeded in seeing, okay, 5 bytes changed, then it interpreted those 5 bytes as a jump instruction, and it's saying, okay, well, in this case, that's jumping to this address, 10, blah, blah, blah. And then if it knows where that address is residing, it'll say. So that appinit hook.dll, this was actually the original thing that I adapted in Life of Binaries to do the import address table hooking. So we just talked about import address table hooking. We said we saw that in Life of Binaries, right? We said it hided, right? Hid. Yeah, so my brain's going too. It hid calc.exe from task manager. But actually, I adapted that from a thing called appinit hook.dll, which is on codeproject.org. The original version actually used an inline hook, and it placed a jump instruction in NT query system information rather than doing an IoT hook. So this is the original version of that, and here it's successfully saying, okay, I can tell that this jumps into the module appinit hook.dll. All right. So that's the overall interpretation. You've got a process, just to sort of say this is the process's module space. Here's everything that's here. You've got the actual DLL where that changes, and that could be, you can have taskmanager.exe, taskmanager.exe, if it were actually hooking in task manager. But here it's just hooking DLLs. So process, module, function, which is being hooked. Sometimes it'll know the name, sometimes it won't. Bytes which are changed, and if appropriate, the location which it's targeting. So in all these cases, it couldn't actually tell where it's targeting. So that could be, again, where they dynamically allocated memory, or they could have hid their DLL by doing like a decom attack to unlink a DLL from the list. Right. These are all, so that's the thing. All the changes Gmer reports are potentially malevolent changes, but if it's not something associated with a known rootkit like Hacker Defender, it now becomes on you to determine whether these are malevolent or not. The reason why is because, as we just saw, things like Zone Alarm, things like Trusted Rapport and Daemon Tools and all those make these sort of changes. So you can't just say, oh yeah, well, there should never ever be inline hooks. Well, unfortunately, third-party security software and other things, just tools that, hack capabilities onto your system, they make these sort of changes, and so it becomes ambiguous. Are these malicious or are they not? The only way to find out is to first try to associate them with some module, and if you trust that module, then okay. Maybe it's some malware pretending to be that module, but there's always how low you can go and how much trust you're willing to gain for the amount of time expended and effort for reversing and all that sort of thing.
Is there a search option in Gmars? Say like, I want to look for memory address so-and-so with that piece of anyone else?
Right, so is there a search option? No. Pretty much the way it works is by default, it's searching by default on everything, and if it can find it, it tries to fill it in. You saw there was that one case before where there's a hidden process where it didn't quite link up the fact that those things corresponded. But pretty much, if it can find it, it fills it in. Otherwise, I don't believe there's any search. All right, so that was the description of the inline hooks. And then we're going to go back and describe the one inline hook which you wouldn't see if you restarted the system. So this one specifically, NT-kernel RTL unwind plus DDC. It's just saying the closest symbol I can find at the, okay, it's saying the actual change occurs at address, say, 8052E4. That's where the actual change occurs. It's trying to help you out by saying, all right, well, I think that looks roughly like this symbol, NT-kernel PIA. So it's saying it knows it's in the NT-kernel memory space somewhere. It's saying the closest thing it could find is RTL unwind, real-time library unwind, which I don't know what that does. But it says it's plus DDC, so that's pretty far away from the start of the symbol. So this change is not necessarily associated with that symbol. It could just be something past it where it doesn't have an actual symbol there. So it's saying it sees 6-byte change at that location, and it's a jump to a specific address, F3B1, blah, blah, blah. But now here it's done that automatic search, and it says, all right, I think that is associated with SQL and Windows System32 drivers, debugv.sys. Right? And so you don't know inherently, looking at this change, is that malicious, is that good? Right? Now you have to go investigate debugv.sys, or Google it, try to see if it has a digital signature, do whatever other mechanisms you can. But I can tell you, at least in this case, that this particular change is due to debugv. So this debugv.sys, there's this debugv tool where I just started it up, and whenever I start this tool, it turns out that it goes into the kernel and it puts an inline hook. And all this tool does is, in kernel space, you don't use printf in order to print out stuff that's happening when you're, debugging or developing some kernel driver. You don't use printf, you use debug print. And so what this thing does is it just goes in there, it loads this, when you double click on the exe, it drops out this debugv.sys, loads it into kernel space, hooks at the debug print. So I think this thing just doesn't have the appropriate symbols, but I think in some versions it will correctly tell you it's hooking debug print function. And so it's hooking debug print so that it redirects to the debugv.sys, and then the debugv.sys takes whatever the input to debug print is, and it sends it down to user space, and then it prints it out in user space. So this is a way that you can see debugging messages in user space without having a kernel debugger attached or anything like that. And so it's a useful utility. It's from sysinternals, but it made a change to the system where it would have been ambiguous as to, why that change was there. And you could go search and, try to find, like, where is this auto-loading, for instance? Like, when is it auto-loading? And the answer is it isn't. It only ever loads when the CXE is launched. So if you restart the system and you don't double-click on debug view, this change won't be there. So this would have been one which would be quite difficult to, well, yeah, I mean, you could have tracked it down with, Googling around and stuff, and you could have some level of confidence, okay, this looks like it was related to this, but it was an example where it was a non-persistent thing where if you didn't have that sufficient confidence and you said, hey, it didn't occur on reboot, I don't see that change anymore, like, why was that? Why didn't I ever see that change again? what did the attacker do beforehand that he's not doing now. All right, so that's just one of many, many, many inline changes. I'll just talk about a few miscellaneous things here before we go for lunch. So miscellaneous in Gmer. This right here, it's saying .sptd2. It's saying the name. So it's saying there's a section .sptd2. There's a driver sptd.sys. And then this is just a heuristic that Gmer has built in where it says the entry point is in this .sptd2. So we said in the P file there's an address of entry point field in the optional header. That says, when the OS is done fixing everything up with the relocations and stuff, it just jumps to this entry point in the code. Like I said, by default, most compilers set that code section to .text section. So Gmer is saying, okay, this is a little bit suspicious because we've got something where the code starts out in a section other than .text. And in this case, it happens to be, quote, legitimate, but we'll come back to talking about this some more later. This is Daemon Tools one of its kernel components. And Daemon Tools looks a lot like a rootkit. It's pretty much indistinguishable from a rootkit in terms of the stuff it does. I guess not so much Daemon Tools, but this third-party library that they bring with them, this sptd.sys, which I can't remember what it stands for. So this thing right here actually is the thing which really wigged me out when I found this on someone's system one time. It also has this component where it creates this randomly named file. Randomly named file, and according to Gmer, the system cannot find the file at the path specified. So randomly named file where if you go look on the file system, it's not there. You reboot, you get a new name, it's not there on the file system. So it's clearly hidden on disk, but it just happens to turn out to be associated with Daemon Tools. And similar thing with this sptd.sys. It was again a heuristic where it's saying, look, I can't find this file on disk, either because it's being locked, like someone is not, it's there on disk, but I can't access it, I can't read it because it's locked, which is, something sometimes they do for protection. They'll lock down their thing and open a file handle so no one else can open it. Or sometimes they'll just say, I can't even find that path. All right, so that was, so we just talked about sort of 3 things. I'll come back to this a little bit when we come back after lunch, but those were sort of the 3 types of changes that we would know a little bit about from previous classes. Inline hooks, just from the sense that we know instructions, we know jump instruction is jumping off to some other code, and typically you're not going to write a function that immediately jumps to some other function as the very first instruction. So that's kind of an illegitimate change that's very common. The jump instructions at the beginning of code, or even depending, code should just not change when it's in memory versus disk unless it's explicitly polymorphic. IAT hooking from Life of Binaries, we even showed an example of that, and IDT hooking. So interrupt descriptor table. We saw Shadow Walker hooking the interrupt descriptor table to try to do this manipulation of the TLB, and then also call gates, which was just a tacked on subject that I threw into Intermediate x86 this year just so I could talk about it again there. All right, any questions on these first few things that we've seen with Gmer? So IDT hooks, IAT hooks, inline hooks, call gates. What the point of them is, what Gmer is saying about them. All right, then back at 1 o'clock.